Hello students, how are you? So, in the previous class we have studied about the quantum numbers. So we'll get a quick revision of that so that we can focus on today's class, which is mainly focusing upon the shapes of atomic orbitals plus the energies of the orbital, right? So yesterday we have seen four types of quantum number. The first one is the principal quantum number. So it is basically related to their energies. See, as we have seen this quantum number earlier also. So when we are seeing that okay, something is in the first shell, it is in the second shell, or it is in the third shell, so that the number we are talking about are here the principal quantum number. So that number is referred to as the principal quantum number in the quantum mechanical model. Okay, clear? So this principal quantum number, it will give you the size of the subshell. So it will give, of course, the energy of the subshell. In addition to that, it will also give you the size of the subshell. That what will be the size of subshell? We will see the meaning of this. So when you are talking about say hydrogen or hydrogen-like species, the size of the orbital only depends upon what? Like n. Okay, it only depends upon n. Of course, when it is for higher electrons, or you can say multi-electron, this trend varies. Means it of course now also depends upon principal quantum number, but there are many factors like electron repulsion and attraction and all of those that will totally decide the size of the orbital. Clear? Then, if you talk about KLMN, so you have heard this terms KLMN, so they only refer to n. Okay, 1, 2, 3, 4. So all the orbitals of a n constitute single shell of atoms and are represented in the following way. So this is just a way of representing, that is KLMN, which each value of n has 1, 2, 3, 4. Clear? Now the most important thing here is that so as we increase the value of n, we go on increasing the value of energy also. Okay, we go on increasing the value of energy also. Means higher the value of n, the greater is the energy of that system. Okay, so or you can say the shell. Clear? Got it? Now next is the size of the orbital. Okay, size of the orbital is dependent upon m. The same thing is written here. Okay, that thing only repeated. And in other words, the electron will be located away from the nucleus. So what does it mean? So as we go on increasing the value of n, the size increases. The size of the shell increases. Okay, the size of the shell increases. You must have seen the model of atom in which we have rings. Okay, we have rings, and along the rings gets expanded more and more as we increase the value of n. So therefore, the distance between the electron and the nucleus go on increasing. Clear? Okay. Now since as initially they were closer. Okay, so for smaller value of n, the electron were close to proton. So there was a force of attraction, greater force of attraction, because it is an electrostatic force and it is totally dependent upon the distance, right? So if it is closer to the nucleus, if the electron is closer to the nucleus, means there is more attraction, and attraction always resembles lowering of energy, because as we have more attractive forces than repulsion, means the energy is lower. Clear? Okay, there is a lowering of energy. But as we go on increasing the value of n, the distance between the electron and the nucleus increases, and hence the attractive force reduces. Okay, means the attractive force between the proton and the electron reduces, and at the same time the electron will have more effect from the neighboring electron, and neighboring electron will do what? They will be responsible for repulsion, because electrons are negatively charged. As all electrons are negatively charged, so they will repel each other. So repulsive forces will dominate than the attractive forces as we go away from the nucleus, and that is the reason we get a increase in the energy. Okay, we get a increase in the energy. Next, talking about the azimuthal quantum number. So what is azimuthal quantum number? So the n decides the size of the orbital, right? The size of the shell. Okay. Now in the shell we have subshell, which is denoted with the help of azimuthal quantum number, and the shape of the subshell is decided by this azimuthal quantum number only. Clear? Now it is also known as orbital angular momentum or subsidiary angular momentum. So what does it define? It defines the three-dimensional shape of the orbital. So we have different shapes for different value of L. Now if I talk about the number of subshell in a shell, then it is simply is equals to n. So whatever will be the number of n, what will be the principal quantum number, that will be the number of subshell. Now its values are different. So talking about its values are different. So suppose if I talk about the first subshell, if I talk about the first shell, it will have one subshell only, but the value or the notation allotted to it is 0, and that is decided how? That is decided on the basis of n minus 1. Okay, so 0 to n minus 1. So if you have, suppose if you have a value of n, then your value of L will span from 0 to n minus 1. Suppose if you have value of n as 2, then you will have 0 and 1, because 2 minus 1 is 1 and 0 to 1 is 0, 1. Similarly, if your n value is 3, so n is equals to 3, so n minus 1 is equals to 2. So your n minus 1 is 2, and starting from 0, we can have 3 types of L values: 0, 1 and 2. Clear? Got it? So if you see here, then you are starting from 0 and you are stopping at one value less than n. So you are actually having the same number of subshell as subshell. So you can remember in this way also that you are starting from 0. Okay, you are not starting from 1, you are starting from 0, but you are ending 1 before. You are starting 1 before and you are ending 1 before. So you will get the same number of subshell as is the value of n. Clear? Okay, now each shell contains one or more subshell or sublevel, so as I have told you, and that value is equals to the value of n. Now if I talk about the values that is related, or the subshell that is related to each value, so for 0 we have S subshell, for 1 we have P subshell, for 2 we have D subshell, similarly for 3 we have F subshell, for 4 we have G subshell, and for 5 we have S subshell, and so on. So this is the value of subshell, and that is these are the related subshells to that. Clear? So as I have told you that if I have n value is equals to 1, then it will have only one subshell whose value will be equals to 0. Means it will have only S subshell. Next, if you have the value of n is equals to 2, then L will span from 0 to 1. Okay, means we will have S and P as the subshell in case of second shell. Okay, in case of second shell. Clear? Now if I talk about the third, n is equals to 3, so it will have 3 subshells. Those will be S, P and D. So in this way, what you will do, you will go on increasing the value of shell. Clear? So each subshell is assigned a quantum number that is known as azimuthal quantum number. So S is assigned 0, P is assigned 1, D is assigned 2, F is 3, G is 4, H is 5, and so on. So all these values of L are azimuthal quantum number or orbital angular momentum quantum number. Now next is magnetic quantum number. Okay, next is magnetic quantum number. So what is magnetic quantum number now here? So within each subshell we have a number of orbitals. What we have? We have a number of orbitals, and the number of orbitals is given by the formula. So if you talk about L, so it is, so if you have the value of L as 0, then you have 2L plus 1 value of what? Orbitals. Clear? So if you talk about S subshell, then S subshell will have a value of L is equals to 0. That will give you only one orbital. Okay, only one orbital, and its value will be 0. So for assigning the number to this orbitals, what you will do? You will start from minus L to plus L. So if your L value is 0, then you will have what? Then you will have only one orbital, that is 0. Okay, that is having a value of magnetic quantum number as 0. Next, if you have a value of L as 1, okay, if your L value is 1, then you will start from minus 1 and go to plus 1. So minus 1, 0 and 1. So that means 3 orbitals are possible. So we'll start from minus 1 and go to plus 1. Okay. Next, similarly, if you have say 4 as the value of L. Okay, 4 as the value of L. Now, if I am saying that if you are taking L is equals to 1, so we are getting 3 orbitals. So we are getting 3 types of p orbital, right? 3 types of p orbital. Now we will talk about those orbital in proper in the next in this class after the we have completed this, say, our quantum numbers revision. Okay, because this is important. So it is important to get an idea about the quantum number. You will use it to and fro in the upcoming chapters also. Clear? Okay. Now we will start from minus L, go to plus L. So that will give you the number of that will give you the orbital value. Okay, orbital value, that is -1 or -2, 0, -2, -1 in case of p, sorry, d, starting from -1 in case of p, starting from 0 and ending at 0 in case of s. Clear? Okay, so the illustration is given here. So if you take the value of L is equals to 0, then the only permitted ml value is 0. Clear? So you will have only one orbital, that is s orbital. Next, if you have L value as 1, then ml can be having -1, 0 and 1 plus 1. So these are the three possible orbitals. Okay, and these are the three possible orbitals. Now in case of L is equals to 2, that is for d orbital. So if you take out the number of orbital, it should be, sorry, for d subshell, if you take out the number of orbitals, then it is equals to 5. 2 to the 4 and 5. Clear? And what is the value of ml? Start from -2 and goes to +2. Now it should be noticed here that the value of L is derived from N and the value of ml is derived from L. So you are getting a relation between all of this. So here is a notation for that. So it's a summarization for that. So if you are taking a value of L as 0, then you will get subshell notation as S and number of orbital will be 1. If you take the value of L as 1, then you will have P subshell and the number of orbitals inside the P subshell is 3. Similarly, for 2 it is D and 5 is the number of orbitals, 3 it is F is the subshell and 7 is the number of orbital. Clear? Now, next is spin quantum number. So we have got the orbitals and each of this orbital will have 2 electrons. Okay, each of these orbital will have 2 electrons and both of these electrons will have opposite spin. Okay, opposite spin is a different thing. So you can't think of the spin, you think about top. So it is not like top. You have to heard the word let to, or you can think of any rotating thing. Okay, like your Beyblade and all. So you don't think of electron as those spinning particles. They don't actually spin. So it is just an intrinsic property of that electron. So it is just an intrinsic property of that electron, or you can say it intrinsic angular momentum, right? So it does not revolve around its axis. So this thing is initially it was believed that okay, it is revolving around that axis, and later on it is busted. This methodology is busted, and we say that it is not the rotation, it is basically the intrinsic orbital angular intrinsic spin angular momentum. Clear? Okay, so how was this predicted? How it was predicted that we have spins, different spins? So in case of multi-electron system, we have studied that Bohr's theory was failed due to closely packed lines. Okay, so it says that for one subshell we will get one spectra, but it was not so. So with the help of advanced spectroscopy, it was seen that they were getting splitted, and that splitting was explained with the help of this spin. Okay, now so this thing is busted. So this thing that is written here, that electron revolves around spins around in own axis. So this was old theory. Now it is just the intrinsic spin angular momentum. Now spin angular momentum is a vector quantity. So for that reason it can have two orientation, and that is totally dependent upon the axis that you have chosen. Clear? Now this two orientation are plus half and minus half. So we have said that it can have two types of say orientation. Okay, so that can be plus half and minus half. So we tell that okay, for plus half it is clockwise, for minus half it is anti-clockwise. Now if you are representing the electron, then you write it as spin up or spin down. So if you are writing an up headed arrow, then it will have a value of plus half and it is represented as spin up. If you have a value of minus half, it is represented as pinned down, right? So orbital can not hold more than 2 electrons. So if you are asked in the question that what is the number of electron in this orbital or that orbital, you will always answer them as 2. So don't have to get confused that since it is of a higher shell, then it will change. Okay, you don't have to think about it. If it is written that what is the number of orbital in an electron in an orbital, it will be always 2 in irrelevant or irrespective of the orbital you are talking about, right? So this is very, very important. Now the things were sum up. So I have already summed it up. So I will not sum it up again. Now we will move to the shapes of atomic orbital. Okay, we have moved to shapes of atomic orbital, and we have said earlier that this wave function has no physical significance. It is simply a mathematical function of the coordinates of the electron. So this is very, very important line. So if I am saying that this is the wave function, then what it is defining? It is basically defining the coordinates of the electron. Where will be the electron located? And it has nothing to do with the physical nature, right? However, for different orbitals, the plots of corresponding wave function as a function of r are different, and that thing arise to the shapes, because it is basically the plot, or you can think of a function which defines the electron density over a surface, and that thing give you the shape. Clear? Got it? So here is a diagram for you. Okay, here is a diagram for you. So what we have seen, why does this psi r don't have any physical significance? See, if you just plot this psi r against r, right, then it is this is giving a very maxima here. Okay, it is giving a maxima here, which is not possible at all. Okay, which is not possible at all. So if you just plot it for further greater values of say n, then you will also find that this psi is getting to negative, and that is also totally wrong. Clear? Okay, so initially psi square r was considered, initially psi was plotted, then psi gave that the electron density shoots up near the nucleus. So that is wrong. That is totally wrong concept, because that is just opposite, because electrons are not located on the nucleus. Of course they are located near the nucleus, but they are not located inside the nucleus. But this plot is saying that the electron is located inside the nucleus. So this psi r is of no significant importance. Clear? And in addition to that, it was giving a negative value of psi r. Clear? So when we squared the same term, then we got only positive values. But the problem here still rises that we have greater electron density near the nucleus. Clear? So this problem still arises, right? So what do we do in the next part? We will simply multiply this psi square r with r, psi square r with r, and then we will plot. And in that case, we got the actual electron density. Clear? So if this thing is not written here, so if you just plot psi square r versus r, then you will find that the electron density is not shooting up here is here close to the nucleus. Clear? So according to Max Born, this psi square gave you the probability density of the electron at a point. Okay, so it is just a probability density. So why it is giving a higher value near the nucleus? Because there is a very high force of attraction near the nucleus. So it is of a high chance that the negative charge will be found there. But it will not be possible, because electron have an intrinsic property of quantization, that they can remain or they can stay only in a certain energy level. So they are not allowed to move close to nucleus. So that is the reason we got a wrong idea from the psi square. Clear? Okay, so this plots were for what? This plots were for 1s and 2s. Okay, 1s and 2s. Clear? Now, if you talk about the 2s, then you can see here that initially the number of what? If you talk about 1s and 2s, you can see that 1s is decreasing steeply, and then it falls and becomes straight or become collinear with this axis. But in case of 2s, it does not behave such. Okay, initially it falls down, then it again begins to rise, and then again it falls down. So what does this depict? So this falling here, it says that it at this point where the it has touched the origin, okay, or it has touched the zero probability, okay, it says that there is a node here. So this thing is called node. So where the probability of finding the electron is zero, that is called as node. So in case of s orbital, we don't have any nodes, okay. If you see this, now you will see the shape of the s orbital, you will find that they don't have any node. But in case of 2s, we have nodes, okay. So s orbital have no nodes, 1s orbital have no nodes, but 2s orbital does have. Clear? And that diagram that we have seen right now depicts it clearly. Clear? So that thing is called as nodal surface or nodes. Now, if I talk about s orbital, then it was found that n minus 1 nodes are present there. Okay, n minus 1 nodes are present there. So this is a simple formula for finding the number of nodes. It is simply n minus 1. So just do n minus 1. If you have n is the principal quantum number. Okay, n is the principal quantum number. So if you just subtract n minus 1, you will get the number of nodes. Clear? In other words, the value of the number of nodes for 2s orbital is 1. So if you talk about 3s, then it is 3 minus 1. So we have 2 nodes now. Clear? Now, let us draw a boundary surface diagram for this orbitals. Okay. So what we have done, we have plotted a boundary surface diagram. Clear? So here is the boundary surface diagram of 1s and 2s. Now you can see, if you see here, that these are just the plots of it. So what is the meaning of this? So if you take the measurements, then you will find that electrons are not present at one point, but we are getting a density here. Okay, so here you can see the density is very high, so it is kind of forming a spherical shape. But if you took it for 2s, then you will find that in their between we have ring type structure where the electron density is less. Okay, in this position, in this place, the electron density is less, means there is a node that is present here, and this node is called as radial node, and this diagram is called as boundary surface diagram, which we are getting as a function of psi square r. Okay, which we are getting as a function of psi square r. So here, where the electron density is high, there the probability of finding the electron is 90%. Okay, it is 90%. Clear? Now, if you talk about the p orbital, then again, if you talk about the p orbital, then this is the shape of p orbital. So you will get a plot like this. So here you will get electron density, and here you will get electron density, right? So it is forming a dumbbell here. So this is the shape of p orbital. Clear? Got it? Now, since the lobes may be considered to lie along xyz axis, they are referred to as px, py, and pz. So here you can see that this dumbbell shape it aligned along x-axis. Therefore, it is px. In this case, it is aligned along y-axis, that is py. In this case, it is aligned along z-axis, that is pz. Right. So this is the shape of p orbital. So if you just remember previously, we have said that for value of so suppose the value of L is 1 for p orbital. Now it will have what? It will have 2L plus 1 number of orbitals. So the value of L for L subshell is 1. Sorry, for p subshell the value of L is 1. Therefore, it will have 2L plus 1 number of orbitals. Clear? So if you just 2 into 1 plus 1, that will give you 3. So these are the 3 orbitals. Now in each orbital we will have 2 electrons. So I am not saying here now again that here we will have 1 electron and here you will have 1 electron. So that is not the case. Electron is not something like particle that will be present there. But the charge that is being held by this orbital is equals to the charge that is held by 2 electrons. Okay, so in that way you can define it in a much better way. Clear? So this p orbital charge, the charge that is present on this p orbital, is equals to the charge that is present on 2 electrons. Clear? So here we are getting an electron density of 2 electron. Clear? Got it? Now, if I talk about the d orbital, then this is the d orbital here. Okay, d orbital has double dumbbell shape, and these are the 4 shapes. Now d orbital is very unique than any other orbital because it is more diffused. So the diffusing is getting more and more. So initially, if you see, then S was kind of concentrated in one place. It was a spherical will be concentrated. Now if you talk about that p orbital, it is of a larger size. Okay, it is of a larger size, but still the number of electron is same. It means that their shape is getting diffused and diffused more and more. The probability, the boundary surface diagram is getting diffused more and more. So you can't think of this shape as a physical thing. It is not like a bottle or a something like container that is present there. It is actually the electron density that is forming this shape. Okay, so this should be very clear in your mind. So don't get the wrong idea that this is a kind of container or a shape that will contain the electron inside it. No, there is nothing like that. It is just the plot of electron density. The electron density has been plotted like this. Clear? So hence the order and size of energy is 4p, then 3p, and then 2p. Means 4p has the greater size and greater energy, then comes the 3p, and then comes the 2p. Further, like s orbital, the probability of electron density also passes through s. So here you can see a node is present. Okay, so two nodes are present here. Okay, if you talk about simply 3D, then two nodes are present here. Okay, two nodes are present here because the electron density is 0. Clear? The number of nodes is given by n minus 2. Okay, got it? Now, these are the 5d orbitals: dxy, dyz, dxz, dx square minus y square, and dz square. You can see it very clearly that this is what? This dxy, because the lobes are present between the x and y axis. Here, dx y square minus y square. But in this case, the lobes are present along the axis. Means this lobe will be oriented along the y-axis and this lobe will be oriented along the x-axis. Okay, so sorry, for this one I'm talking about this one. So this is dxy. This is dxy. You can see that they are not oriented along the axis, but they are between the axis. Here you can see that they are oriented along the axis, so they are therefore named in a different way: dx square minus y square. Again, dyz are between the y-axis and z-axis. If we talk about dz square, then they are oriented only along the z-axis. Clear? Okay. Now there are 5 values of ml. Okay, we know that there are 5 values of ml. We have calculated those: -2, -1, 0, 1, and 2. So those are assigned to this 5 d orbitals. Okay, clear? Now, what is the number of nodes again here? The number of nodes is given by n minus 2. Okay, in case of say d orbital, it is given by n minus 2. That is, the number of radial nodes is 1 for 3p orbital. So this n minus 2 is for p. Okay, this is for p. So I will give you a general formula, that is n minus l minus 1. So this is the general formula for finding the radial nodes. Okay, so just put this formula n minus l minus 1, you will get the radial nodes. Now what is the number of angular nodes? So there are basically two types of nodes. I am not giving you the exact shape of that. So radial node, you know it. How does it look? So it looks like this. So you will see a ring here. So in case of p orbital also, if we draw the body surface diagram, you will see the ring there also. Clear? So that are called as radial nodes. And here you can see that there is a plane that is having no electrons. Okay, in this and this, between this we have a plane. For s orbital we don't have any plane because it is spherical in shape. So here is a plane in between these two lobes that is having no electrons, and that is called as angular nodes. Here also you can see very clearly that there are two planes here. So between these two lobes there is one plane, and between these two lobes there are two planes, and these two planes are perpendicular to each other, right? These two planes are perpendicular to each other, and these are called as angular nodes. So number of angular nodes is given by n. So whatever will be the value of n, that will be the number of angular nodes. So for d orbital, the number of angular nodes will be 2. For p orbital, it will be 1, and for s orbital, it will be 0. If I talk about the radial nodes, then what is the formula? It is n minus l minus 1. So for, if I talk about say I'm asking that what is the number of radial nodes in case of 4p, you will use the formula n minus l minus 1. The value of n is 4. The value of l is 1 for p orbital, and minus 1. So 4 minus 1 minus 1, that will give you 4 minus 2, 2. So there will be 2 radial nodes. So it goes on increasing. So for 2p we have 0 radial nodes. For 3p, we have one radial node. For 4p, we have again one radial node. So we'll start from that point where the p orbital is started. Clear? Got it? Now, so this is about the shape of the orbitals. Okay. So as I have told you earlier that okay, pz will be aligned along the xz axis, px will be aligned along the y axis, and py will be aligned along the y axis. Clear? Now, if I talk about the lobes that are, or you can say the orbitals which are aligned along the axis are px, py, and pz for p or p subshell, and in case of d subshell we have dx square minus y square and dz square. So these two orbitals are aligned along the axis. Clear? Whereas the remaining 3d orbitals are bisecting. Okay, they are bisecting between the lobes. So you can see here from the diagram. If I just bring the diagram here, you can see that these are the two lobes, right? And we have an axis in between. Similarly, these are the two lobes and we have an axis in between. So this diagram should be remembered. This is very important. So when you will handle this coordination compound and all, then you have to be curious about this thing. Okay, so if you're not aware about the shapes of the orbital, that how are they oriented along the axis, then you will not be able to describe their shape and all. Clear? Okay, so this will form the basis of all. Now, so this is the energy order. Okay, this is the energy order in case of hydrogen atom. So I am talking about the hydrogen atom, and this is a very important question for your exams, competitive exams, because you have an idea of the n plus n rule in case of every system. But if you are talking about the hydrogen atom in which we have only one electron, then what will happen? The electron will have an equal probability of existing in both 2s and 2p. Okay, so let us not get into failing right now. Just wait, or just stick to this energy order. So 1s has the least energy order, then we have 2s and 2p which will have the same energy difference. Okay, not difference, same energy value. Then 3s, 3p, and 3d will have a greater value than 2s and 2p. Then with 4s, 4p, 4d, 4f, 4. Next is the reason. Okay, so this is the order for hydrogen atom. This is very important. So here is the energy diagram for that. So if you look here for hydrogen atom, then this energy plot. So first we have 1s, then 2s, 2p, then 3s, 3p, then 3d. But in case of what? In case of your multi-electron system, you can see that this order is disrupted. So we'll talk about this order, how it is decided. So it is basically the n plus n rule that gives you this order. Now, let us talk about this n plus n rule. So what you will do, you will simply take the value of n and add it with L for a given subshell. Clear? And whatever with the value of n plus L will decide the energy. So the one with a greater value of n plus L will have a greater energy. The one which have a lower value of n plus L will have a lower energy. Now, if two of the subshell are having the same n plus L value, then the one with the lower value of n will have the least energy. Clear? So these are the two things. So if your n plus L value is larger, means then subshell energy is larger. But in case your n plus n value is same, then you have to look upon the n value, and the one with a lower value of n will have the lower energy. Clear? Okay. So although the shape of the 2s and 2p orbitals are different, an electron will have the same energy in 2s orbital when it is present in 2p orbital. So we are talking about the hydrogen atom. Okay. So this was all for today's class. We have seen the energies and all. So I have given you the order n plus L. Okay. So if you talk about a given principal quantum number, so this is the order SPDF. So if you are talking about the specific, you can, if you are saying that, okay, if you are talking about the 3D, okay, then third shell, then you will say that 3s will have the least energy, then 3p, then 3d, and then 3f. So if I'm talking about the given shell, then this is the order. Okay, but if you have multiple shell contribution, then you have to take the n plus L value. Okay, and what is the reason behind it? Why are we seeing this order? For the hydrogen like species, we are saying that okay, they have all the same energies, But as we are moving to the multi-electron system, then this thing is getting disrupted. Because in case of single electron, the hydrogen atom is having only one electron, and we don't have any extra force in addition to the attractive force. We have only the attractive force that is present in hydrogen. But as we move to multi-electron, there is more type of interaction like electron-electron repulsion and all, and that give arises to the you can say removing of degeneracy. So this criteria of having the same energy is called degeneracy. So if you get this electron repulsion and all, then this degeneracy will be removed. Okay. Now, on the other hand, the attractive interaction of the Z effective and all. So what is Z effective here? So what we are seeing, what happens here? So as soon as more and more electrons get involved, the actual charge that would have been felt by the electron due to electrostatic force of attraction by the proton, that is kind of decreased, because in between we have more and more electrons that is disrupting this normal interaction or ideal interaction. Okay. And that gave rise to a new term, that is Z effective. That is the actual charge that is felt by the electron. Clear? Now, this is called as screening effect. Okay. And the actual charge that is being experienced by the electron after it is being disrupted by the inner electron is called as effective nuclear charge. Okay. Now, despite this you can say repulsion, the attractive force experienced by the outer shell electron increases with increase of nuclear charge. Okay. In other words, we can say that the energy of interaction between the nucleus and electron decreases with the increase of atomic number. Further, within a shell, due to the spherical shape of the s orbital, the s orbital electron spends more time. Now, let us talk about which will shield more. So we have seen that the inner electrons are shielding the outer electrons. Now there is an order for this screening, that which will shield more. So the order is simply the order of L. The one with a lower value of L will have the largest amount of shielding. The one with a smaller value of L, greater value of L, will have the least amount of shielding. Means the s orbital is the one which is having the maximum capability of shielding. And of course, this goes to the shape of the orbital. If you look at the shape, it is totally spherical in nature. So you are getting a shield. It is acting as a shield from all direction. Okay, so that is the reason that is showing the maximum shielding effect. Then comes the P, and as the shape go on diffusing and diffusing more, you will get a less shielding, or you will get a pure shielding. Clear? The same thing is written here. It depends upon the value of N plus L both. Now, what is the role of N here? So smaller is the value of L, greater is the shielding. Now, greater is the value of N, smaller is the shielding. Okay, so in both cases it reverses. Okay, so smaller N and smaller L. So the smaller N and smaller L will give you more shielding as compared to the bigger N and bigger L. Means shielding effect is inversely proportional to the value of N and also inversely proportional to the value of L. Clear? Now, this N plus L rule, as I have told you, the one which having a lower value of N plus L will have a lower energy. The one with having a higher value of N plus L will have a higher energy. And if two are having the same N plus L value, then the one with a smaller value of N will have a lower energy. Clear? So you can just verify this thing. Okay, if you just look at the order, you can verify this thing. Clear? Okay. Now, if I talk about the energy of 2s orbital, then the hydrogen energy means the 2s orbital of hydrogen is more. Then we have lithium, smaller value of lithium, then we have sodium, and then we have potassium. Clear? So with this, I end my lecture. Thank you.